Hi, this is Professor Amanda Sartor, and I'm going to be working out some problems related to exponential and logarithmic functions. The first question says, sketch the graph of the exponential function. Our function is f of x equals 2 to the x. What makes this an exponential function is having that variable in the exponent. So the x is the exponent, 2 is called the base, which is what the exponent is attached to. So the question first wants us to fill in this table of values. So it's giving us a group of x values, and we're supposed to find the y values. So I'm going to redraw the chart right here. And in for x, we're substituting -2, -1, 0, 1, and 2. And we're going to find the y values. So let's start with the easier values of 1. So if we substitute a 1 into the equation, that would give us 2 to the 1. 2 to the first power is 2. Then we'll substitute a 2. That's 2 to the second, which is 4. 2 to the 0 is 1. 2 to the -1. Having a negative in the exponent means reciprocal of the base. So the reciprocal of 2 is 1/2. And we have 2 to the -2. So we've got a negative, so it's going to be reciprocal, but this time I still need to square it. 1/2 squared would be 1/4. I'm going to plot these points, and my points are 0, 1, 1, 2, 2, 4, got -1 1/2, -2 1/4, and I'm going to connect these points. These points seem to connect very easily, nice and smooth. Now we think about what's happening if we want to continue this line. So what I'm saying is if I choose values along this path here, -1, -2, like -3, what's going to happen is we'd get -1/8, not -1/8, +1/8. So what's happening is this curve is getting closer and closer and closer to 0 without ever touching it. And because that's happening, we have an asymptote, a horizontal asymptote that is right on top of the x-axis. That's a horizontal asymptote at y equals 0. On the other end, if we think about on this side of the axis, where our x's are getting larger and larger, for instance, if x was 3, y would be 8. So this portion of the curve is blowing up to infinity very quickly. And so looking at these graphs, it looks like answer choice D is the right one. The next question says, use the graph of y equals 3 to the x and transformations to sketch the exponential function f of x equals 3 to the x plus 5. Determine the domain and range, also determine the y-intercept, and find the equation of the horizontal asymptote. Okay, so we want to graph the equation f of x equals 3 to the x plus 5 by using transformations. In order to graph with transformations, we have to know what the starting graph looks like, that 3 to the x. So let's take a minute and graph 3 to the x. So I'm going to choose for x -2, -1, 0, 1, and 2. I'm going to substitute these values into the equation 3 to the x to see what those y values are. So I'll start with the easy ones first. 3 to the first is 3. 3 to the second is 9. 3 to the 0 is 1. 3 to the -1. -1, or having an exponent that's negative, you're going to do the reciprocal of the base. So the reciprocal of 3 is 1/3. 3 to the -2 will be But because of the negative, we're going to have the reciprocal of 1/3, and then we need to raise it to the second power. 1/3 to the second power will be 1/9. So now we know we have some ordered pairs, and we can sketch what the graph looks like. So we have 0, 1, 1, 3, 2, 9, -1 1/3, -2 1/9. So this is what the curve looks like. We do have a horizontal asymptote that is along the x-axis or at y = 0. And so now we have an idea of what 3 to the x looks like. And then we want to know what f of x equals 3 to the x plus 5 looks like. So this plus 5 is a transformation. And because it is adding 5, we know that that is going to be a shift. And because it's on the outside, it's a vertical shift. And because it's a plus, we know it's going to go up, and plus 5, up 5. So if we take this graph over here and shift it up 5 units, we're going to get our graph. So instead of crossing at 0, 1, we're going to shift that up 5 to being at 6. This point right here, which is 1, 3, will go up 5 to be at 8. 1, 8. I'm sorry, is that right? 3 plus 5 is 8. Yeah. Okay, and then on the other side, we have this point right here, which is at 1/3. So if we take 1/3 and move it up 5, I can't do that math in my head very easily. 5 plus 1/3, well, that's 5 1/3, which is the same thing as 16/3. So that point will go to -1, 5 1/3, so maybe about right here. That horizontal asymptote that we talked about that was at y = 0 will also get shifted up 5. So from 0, it'll get shifted up to 5. Now we have a horizontal asymptote at y = 5. So then we can draw the curve, and we get this picture right here. Now, going back to the directions that we were given here, it says use the coordinates of the 3 points of the graph y = 3 to the x to determine the corresponding points on the graph of f of x equals 3 to the x plus 5. We did this. We figured out the original points over here. We had -1 and 1/3, and that's what they gave us here. 0, 1 was another point, and 1, 3 was another point. And we showed where those points moved. Those points moved up 5 spaces. So this 1 moved up to a 6. The 3 moved up to an 8. And the 1/3 went to 5 1/3, or 16/3. Okay, let's check what else they asked us to do here. Determine the domain and range. So when I find domain, I hold my ruler vertically, and I go from left to right. And as you go from left to right, you'll notice with this graph, the first time you hit would be at -infinity, and the last time you hit is at +infinity. So the domain of our function is all real numbers or -infinity to infinity. And that's going to be the case with all exponential functions. They have a domain of all real numbers. For the range, I'm going to hold my ruler horizontally and go from bottom to top. The first time you hit the graph will be just after that horizontal asymptote at 5, and then it goes on to infinity. So the range starts at 5 and goes to infinity, and we're going to use a parenthesis on the 5 because our graph is never going to reach the asymptote. It'll get closer and closer but never reach it. All right, so what else did it ask? Determine the y-intercept. Okay, to find a y-intercept, you let x equal 0. So our function f of 0, 3 to the 0 plus 5, 3 to the 0 is 1, 5 plus 1 is 6. So that is our y-intercept, and that's also the point that we found earlier here. All right, so we found the y-intercept. What else? Find the equation of the horizontal asymptote. That's what we found right here. So it started off at y equals 0. We shifted it up 5, became y equals 5. So the equation of our horizontal asymptote is y equals 5. The next question says, suppose that you have $3,000 to invest. Which investment yields the greater return over a 10-year period? 7.25% compounded daily or 7.3% compounded quarterly. So in this problem, we're going to use a formula for compound interest. This is the formula. A equals P times 1 plus R over N to the NT. Let me go through what each thing stands for. The P is principal or initial amount of money. Your starting amount is the principal. And we have R, that's going to be your rate, your interest rate. We're always going to write this in decimal form. The T is time in years. The N is the number of compoundings in the year. We'll talk about that more in a minute. And then A, that is going to be your accrued amount or your ending amount. So in this question, it says you have $3,000 to invest. That's going to be our principal or initial amount of money. And it's over a 10-year period, so our time is 10 years. And we have two options. We have 7.25 compounded daily or 7.3 compounded quarterly. So for option 1, which is our rate being 7.25%, and remember we're always going to write this in decimal form, so I'm going to move that decimal point over 2 places. And this is compounded daily, and this is how often interest is added. So this is going to tell us that our value of N is 365, because that's how often the interest would be added. Our option 2 is going to be an interest rate of 7.3%. Let's move the decimal point over 2 places to put it in decimal form. And that's compounded quarterly, which means N will be 4. Quarterly is 4 times a year. So what we want to do is use our formula of A equals P times 1 plus R over N to the NT with these 2 different options. So let me erase what all these mean. And let's work out option 1. That's going to be A equals 3,000 times 1 plus 0.0725 over 365 to the 365 times 10 years. We're going to put that in a calculator, and then for option 2, we have 3,000 times 1 plus 0.073 over 4 to the 4 times 10. Okay, so I got my calculator out to type this in. I'm going to type the whole thing in, 3,000 parentheses times 1 plus 0.0725 divided by 365, close parentheses. I need an exponent. Some of you have older calculators, may need to type parentheses around this. 365 times 10, close parentheses. The parentheses are to make sure you're putting all of that in the exponent. Hit enter. And let's see, we've got 6,000, oops. All right, let me fix that. $6,193.75. We're rounding to the nearest cent. Okay, so like I said, that came out to be $6,193.75. But I wanted to show you, just in case you don't have a fancy calculator like this, I'm going to clear this out. And if you don't have a calculator where you can just type that whole expression in, you can still do this. You are going to just need to follow order of operations. So with order of operations, you're going to start on the inside first. You're going to do that division first. Then you're going to add the 1. Exponents come before multiplication, and then we'll finally do that multiplication. So let me show you how to type that. Okay, so we would do 0.0725 divided by 365, enter. Then we're going to add 1, enter. Then we need to do our exponent. And I probably would go ahead and do that multiplication. 365 times 10 would give you 3650. And then finally, you're going to multiply that by 3,000. And you can see we got the same answer, the $6,193.75. Okay, so let's do the same thing with option 2. We've got 3,000 times 1 plus 0.073 divided by 4, close parentheses, exponent, 4 times 10. Oops, I didn't do an exponent. So let me delete this. All right, so then we have exponent, 4 times 10. We get $6,184.41. And since option 1 came out to be a larger amount, that's going to be the better investment. And you would choose 7.25% compounded daily. All right, our next problem is an application problem. Typically, weekly sales will drop off rather quickly at the end of an advertising campaign. This drop in sales is known as sales decay. Suppose that the gross sales S in hundreds of dollars of certain product is given by the exponential function. S of t equals 6,000, 2.5 to the negative 0.7t, where t is the number of weeks at the end of the campaign. Answer the following questions. What was the level of sales immediately after the end of the ad campaign when t equals 0. So we want to take our function that represents sales, S of t equals 6,000 times 2.5 to the negative 0.7t, and in that first part, we're wanting to let t equals 0, finding S of 0. S of 0 will be 6,000, 2.5 to the negative 0.7 times 0. That's going to give us 6,000, 2.5, 0.7 times 0 is 0. 2.5 to the 0 is 1, and 6,000 times 1 would be 6,000. So sales immediately after the end of the campaign would be 6,000. Okay, so we'll do the other parts using the calculator. What was the level of sales 1 week after the end of the advertising campaign? So that would be finding S of 1, letting t equals 1. So that would be 6,000 times 2.5 to the negative 0.7 times 1. I'll put that in my calculator. That's 6,000 times 2.5 in the exponent, negative 0.7 times 1. And then I'll close parentheses. So that gives me 3,159, and I'm looking at my directions here. It says round to the nearest whole number, and that 3,159 would be the nearest whole number. Then the next part says, what was the sales level 2 weeks after the end of the advertising campaign? So that's S of 2. Substituting a 2 in for t, 6,000 times 2.5 to the negative 0.7 times 2. My calculator, 6,000 times 2.5 to the negative 0.7 times 2. That gives me 1,664 if I round to the nearest whole number. Okay, the next example says, suppose your great-great-grandfather invested $400, earning 5.5% interest, compounding continuously 100 years ago. How much would his investment be worth today? So this almost seems like you would be doing a compound interest formula, but we have a key word here of continuously. So that this formula is a little bit different. It is A equals P e to the RT, where P is that principal or initial amount. R is the rate, the interest rate, which you're going to write in decimal form. T is time. And A is your accrued amount or your ending amount. And E is not a variable, it's a constant. E is approximately 2.718, and those decimals continue on forever, sort of like pi. If I go onto the calculator here, I do have an E button. There's E, and there's the 2.718 with the decimals continuing on. So that's the formula that we're going to use. And remember, the key word here is continuously. That's what tells us to use this particular formula. So let's identify the different values in this problem. it says that your great-great-grandfather invested $400. That's going to be your principal. Excuse me, I'm sorry, I'm just having trouble. The principal is 400. The interest rate, 5.5%. 5.5%. We're going to put that in decimal form, 0.055. And compounded for 100 years. That's our time. So t equals 100. So we'll substitute that into our formula. A equals 400 e to the 0.055 times 100. We'll plug that in the calculator. We'll get 400. And I'm going to use this E button right here. I hit the second and natural log button. That gives me e to an exponent instead of just an e. So I'll do 0.055 times 100 in that exponent. So my great-great-grandfather's investment grew to be $97,876.77. That is the power of compounding and time. The next question says, solve the exponential equation using the method of relating the bases. First, by writing the equation in the form b to the u equals b to the v. Okay, so what those directions are referring to is this property called relating the bases. If you have an equation that is in this form, b to the u equals b to the v, then we can say that because the two bases are equal to each other, the only way these expressions can be equal to each other is if those exponents are equal to each other. So we're able to draw the conclusion that u equals v, giving us a much simpler equation to solve because the bases are gone. So in this example, we want to solve the equation 3 to the x equals 243 with this property in mind. So we start off with 3 to the x equals 243. So remember, my goal is to write it in this format here. A base to a power equals same base to a power. Now I have on the left side of the equation a base to a power already. So I'm going to try to take advantage of that. My base is 3. I want to have the same base on the other side. Okay, so I'm going to start to think of powers of 3. 3 to the first power is 3, 3 to the second power, 3 to the second power is 9, 3 to the third power is 27, 3 to the fourth power is 81, 3 to the fifth power. Now you guys don't have to have these in your head. You're going to be able to use your calculator to work it out, and it works out that 3 to the fifth is 243. So because of this, 243 and 3 to the fifth are equal to each other. I'm allowed to change that 243 to 3 to the fifth. 3 to the x equals 3 to the fifth. Now that I've written this equation so that the bases are the same on both sides, I know that the exponents have to be equal to each other. So x is equal to 5. So that allows me to reduce the equation down, and this is an equation that's already solved. X equals 5. Okay, the next problem says solve the exponential equation by the method of relating the bases. First, by writing the equation in the form b to the u equals b to the v. So we want to write both sides of the equation with the same base, so then we can say that the exponents are equal to each other. So our equation is 49 to the x equals 1/7 to the x minus 4. So I've got 49 to the x equals 1/7 to the x minus 4. I want to make the bases the same, and I know 49 is a perfect square. 49 is 7 squared, and I've got 1/7 over here, so I'm thinking about trying to make these both a base of 7. So let me rewrite 49. 49 is the same thing as 7 squared, and the x just carries down. 1/7 is the same thing as 7 to the negative 1. Having a negative in the exponent is reciprocal of that base. And then we're going to simplify using some properties of exponents. There's a property of exponents that says if you have b to the power of m to the power of n, so a power to a power, then you multiply those powers together, b to the m times n. So I've got 7 to the second to the x. I'm able to multiply those together to get 7 to the 2x. The same thing happens on the other side of the equation. 7 to the negative 1 to the x minus 4. And I'll multiply those powers together to get 7 to the negative 1 times x minus 4. So now I've written both sides of the equation with the same base, so I'm able to use that property called relating the bases to say that this exponent on the left is equal to the exponent on the right. So this gives me a new equation to solve. I'll distribute that negative to get negative x plus 4. Add x on both sides. That gives me 3x equals 4. And divide both sides by 3, and x equals 4/3. Solve the equation, the exponential equation, using the method of relating the bases by first rewriting the equation in the form b to the u equals b to the v. So we want on both sides to have the same base so that we're able to simplify the equation saying that this exponent is equal to this exponent. So my equation is 2 to the x cubed equals 16x over 8 to the negative x squared. Looks a little bit messy, but we're going to take it step by step. So this question is 2 to the x cubed, 16 to the x, 8 to the negative x squared. So on the left, I've got a base of 2, and 16 and 8 are also powers of 2. 8 is 2 to the third, and 16 is 2 to the fourth. So I'm thinking that that's the base that I want to use. So that's leaving the left-hand side alone. And on the right, I'll start changing these numbers to a base of 2. 16 is 2 to the fourth. Carry down that exponent of x. 8 is 2 to the third, and carry down that exponent of negative x squared. Now I'm going to use the power rule and simplify this by multiplying the exponents. So that becomes 2 to the 4x. I can use the power rule right here, multiplying these exponents. And that becomes 2 to the negative 3x squared. On the left-hand side, I'm just carrying that down. It's not changing. So on the right-hand side, I'm going to use a property called the quotient rule. The quotient rule looks like this. If you have b to the n over b to the m, so you're dividing when things have the same base, what you do is subtract the exponents. So that's what's happening over here, where we have the same base and we're dividing, so we're going to subtract those exponents. So the left-hand side stays the same, the right-hand side becomes the numerator exponent minus the denominator exponent. That's minus a negative. So continuing, minus a negative is a plus 3x squared. And I have the base is the same on both sides, so those exponents have to be equal to each other. X cubed has to equal 4x plus 3x squared. I'm going to move all the terms to the same side. So when these terms move over, they change to negative. I'm going to solve by factoring. There's a common factor of x. Becomes x squared minus 3x minus 4. Continue factoring the quadratic. X and x, 4 and 1, the minus and a plus. Then we can set each factor equal to 0 using the zero product property. And we get x equals 0. Add 4 to both sides to get x equals 4. Subtract 1 on both sides and get x equals negative 1. So we got 3 solutions, 0, 4, and negative 1. The next problem says write the exponential equation, as an equation involving a logarithm. So what we need to know is that exponential equations and logarithmic equations, these are inverses of each other. So they're related. We need to see how they're related to each other. So if you have an equation like b to the x equals y, this is an exponential equation. This can be written in logarithmic form by writing the word log, and the base of the exponential is going to be the base of the log. So that becomes a b there. The log always equals the exponent. So the exponent here is going to be what that log equals. So that's x. And then what our exponential equals, that's what goes inside the log. So this is how exponential and logarithmic equations are related. So we need to memorize this comparison. We need to memorize that the log always equals the exponent. We need to memorize that what's inside the log is what the exponential equals, and that the base of the exponential is the base of the log. So going over to our example is 5 to the negative 3 equals 1 over 125. So if I want to write this as a log expression or equation, I write the word log, and then that log is going to have a base. That base of the log is going to be the base of the exponent. Then the log is always going to equal the exponent. So the exponent is negative 3, and that's what it equals. So the negative 3 goes here. And then what the exponential equals is what goes inside the log. So our log equation, our equivalent log equation, is log base 5 of 125 is equal to negative 3. This example says, use the definition of a logarithmic function to write the logarithmic equation as an equation involving exponent. So once again, we need to make sure that we understand the relationship between logarithmic equation and exponential equation. So anytime we have a log equation, it's going to be something that's like this. Log base b of x equals y. If we write that as an exponential, we're going to notice that the base of the log is b, and that's going to be the base of the exponential. And then the log is always going to equal the exponent. So the exponent on that is going to be y. And then my exponential expression is always going to equal what is inside the log. So that's going to be x. So let's try this with this example here, which is log base f of x minus 1 equals 7. So if I want to write this as an exponential, the first thing I'm going to notice is the base. The base is f, and that is going to be the base of my exponential. The log always equals the exponent. This log equals 7, so 7 is going to be my exponent. And then this exponential is always going to equal what is inside the log, and that is x minus 1. So to rewrite this log equation as an exponential equation, that's going to be the base of f to the 7th power equals x minus 1.